Bismillahirrahmanirrahim. Assalamu alaikum students. Our today's topic is magnitude comparator. Uh, the comparison of two numbers is almost done in most of the operations or when we are going to compare that either mm, which number is greater or equal to which number and which is less than the desired numbers. A magnitude comparator is a combination circuit which compares the two numbers set as A and B and determine their relative magnitude that the outcome of the comparison will be specified by three binary variables which will indicate that either A is equal to B or is greater than B or A is less than B. These three binary variables will be the output of the any magnitude comparator, you can say. And during the algorithm of comparison, we say uh, that an algorithm of direct application uh, for the comparison, as if any person compares two numbers, then we will use that direct algorithm of comparison. In this algorithm, we will consider two numbers. We can say that A and B with 4-bit uh, digits, and we will write their coefficients as are written from in the uh, descending order as A is equal to A3, A2, A1, and A0, and B is equal to B3, B2, B1, and B0. And to compare these two numbers, as first of all, that we have to check that either these numbers are equal or not. And when two numbers are equal, uh, only if and only if all the corresponding bits of the numbers are equal. For example, we can say that if A3 is equal to B3, A2 is equal to B2, A1 is equal to B1, and A0 is equal to B0, then the two numbers will be equal when all these bits are same and equal. The binary variable which is defined by this A is equal to B as shown in this at this stage of output. And this variable will indicate that binary variable is equal to 1 if the input numbers A and B are equal, and this output variable A is equal to B will be equal to 0 if the two numbers A and B are not equal in magnitude. For equality to exist, we can say that exclusive NOR circuit can be used to compare two numbers, and for that purpose, we can say that this will be the equation for the exclusive NOR function. Xi will be equal to AI bi plus AI complement bi complement, and we can say that we can also implement this system by using exclusive OR circuit and taking an inverter at the output of the exclusive OR circuit as seen here: x3, x2, x naught, and x1 and x naught. We can see that xi, and as this is a 4-bit magnitude comparator, then that's why the values of x will be x naught, x1, x2, and x3. And to implement this part of the magnitude comparator, we use the exclusive NOR gates, and their implementation is here by using the AND, OR, and NOT gates. We implemented these exclusive NOR gates, and the binary variable, which is we can say A is equal to B, will be equal to 1 only if all the pairs of digits of the two numbers are equal, and when these are equal, then we have to find out this operation which is equal to A is equal to B will be equal to that x3 into x2 into x1 and x0, that outputs of all the four exclusive NOR gates will be ANDed by using an AND gate, and that output variable is at the output of this AND gate, which is equal to A is equal to B. And this will be equal to 1 only if all the outputs of these three exclusion OR gates x3, x2, x1, and x0 are equal to 1, then this output will be equal to 1, otherwise it will be equal to 0. And now, uh, for the next step, we have to determine that either if we inspect the relative, these two numbers are not equal, then we have to determine either A is greater than B or A is less than B. And to determine, we have to inspect the relative magnitude of pairs of the most significant bits. If the most significant bits we are going to compare here, if the two digits of a pair are equal, not equal, we will compare the most significant bits. And if these most significant bits are equal, then we will check for the next lower significant pair of digits. And this comparison will be continued until and unless the pair of unequal digits is reached. If the corresponding digit of A is 1 and that of B is 0, we will conclude that A is greater than B. A greater than B. And if A is 0 and B is 1, we will conclude that A is less than B. A is less than B. And for these two cases, the sequential comparison can be expressed logically by using these Boolean functions. As we can, know that when we are going to compare the symbols for the output variable of A is greater than B and A is less than B are binary output variables that are equal to 1 when the this will be equal to 1 if A is greater than B, and or this output variable A is less than B will be equal to 1 respectively. Which condition is satisfied, that output will be equal to 1. And we can see that the gate implementation is shown in this figure of 4-bit magnitude comparator, just which is derived from these Boolean expressions. It involves a certain amount of repetition, and unequal outputs can be used by the same gates that are needed to generate the equal output. And this from this logic diagram, it is clear that four X outputs x3, x2, x1, and x0 are generated by using the NOR circuit and are applied to the AND gate to give the output binary variable of A is equal to B. The other two outputs use the X variables to generate the Boolean functions which are listed here. As we know that when we will compare two numbers, we will first we will start from the most significant bit. For example, we say that if A3 and B3 will be compared, if A3 and B3 both are equal, then we will move to the next bit. And if not equal, for example, if A3 is 1 for the this condition of A is greater than B, if A3 is 1 and B3 is 0, then we have to make this, we say that the min term equal to 1. So we may take A3 as A3 is 1 and complement of the B3. And if both are equal, then this will be equal to 0, and we will move to the next significant pair. And for that next significant pair, we will have to compare the A2 with the B2. And if both are A2 is greater than and A2 is 1 and B2 is 0, then we will check out that the only that will be checked if x3 is equal to 1. If x3 is 0, then this condition is not necessary to be fulfilled. And similarly, and when we will move to the, if A2 and B2 both are 1, then this will be also equal to 0, and we will move to the next significant bit. And at that point, we have to check that for the both x3 and x2. If both are equal to 1, then we will check those significant bits A1 and D1. And if those A1 and B1 are equal, then we will move to the next step. And if these two are not equal, and we can say that if A1 is equal to 1 and B1 is equal to 0, then this will show us that A is greater than B. And if both A1 and B1 are equal, then we will move to the next uh, significant bit, which is A naught and B naught. And so we will continue this process further. We can see that in the output variable of A greater than B, we take the complement of the B digits only. And for as we say that A is greater than B, and in that case, A for the A greater than B, A will be equal to 1 and B will be equal to 0. So we take the complements of the B digits, and for the output variable of A less than B, we know that A will be equal to 0 and B will be 1. So for that case, we take the complement of the A digits, and B will be in the unprimed form as seen in this Boolean expression. So by using these Boolean expressions, we can easily uh, construct the magnitude comparator circuit as shown in this figure. And if there is any problem, you can ask questions and comments or WhatsApp me. So students, this is the 4-bit magnitude comparator, and in the same way we can uh, develop generate the higher bit magnitude comparators in the similar manner. So, inshallah, in our next lecture, we will see about the decoders and their implementation and their application. So, study this thing, and we will, inshallah, discuss in our next lecture. Take care. Allah Hafiz. Assalamu alaikum.